Have you ever noticed how some plants still look clean after sitting outside through rain, wind, dust, and mud? Most leaves eventually become dirty. The lotus leaf, however, behaves differently. Water does not spread across it. Instead, droplets form almost perfect beads, roll across the surface, collect loose dirt, and carry that dirt away. What appears to be a simple waterproof leaf is actually a carefully structured surface, one that engineers have studied, copied, and converted into real products. Welcome to the lotus leaf's hydrophobic effect. Today, I will explain how this natural, self-cleaning system works, how it inspired commercial technology, and why reproducing nature is more complicated than simply making something waterproof. At first glance, the lotus leaf looks smooth. Under magnification, however, it is anything but smooth. Its surface contains microscopic bumps covered by much smaller wax structures. These two levels of roughness reduce the amount of physical contact between the leaf and a water droplet. Tiny pockets of air remain beneath the water, so the droplet rests partly on air instead of fully wetting the leaf. This creates what is called a super hydrophobic surface. Hydrophobic meaning water repellent, while super hydrophobic describes an extreme version of that behavior. Water beads up and rolls away with very little resistance. The dirt removal process is just as important as the water repellency. Because particles do not adhere strongly to the rough, waxy surface, a moving droplet can collect them more easily than the leaf can hold them. In their influential 1997 study, Wilhelm Barthold and Christoph Nienhuis demonstrated that water droplets could remove particulate contamination from rough, water-repellent plant surfaces. They named this combination of roughness, low adhesion, and self-cleaning behavior the lotus effect. In other words, the leaf does not actively clean itself, rather, it creates conditions in which ordinary rain can perform the cleaning. One of the clearest commercial examples of this concept is Stowe Color Lotus Sand, an exterior wall coating made by Stowe. And rather than making an ordinary smooth paint surface, the coating creates a highly water-repellent microtexture modeled after the lotus leaf. When rain contacts the wall, it forms droplets instead of spreading into a film. As those droplets run down the facade, they carry loosely attached dirt with them. Stowe introduced its Lotus-on facade paint in 1999, making buildings a useful example of how an observation from botany can be transferred into manufacturing and construction. This is the product I would build the main discussion around because its purpose is easy to understand. A building exterior is constantly exposed to rain, airborne particles, pollution, and biological growth. Cleaning a large facade can require labor, equipment, water, and chemicals. A coating that stays cleaner for longer may reduce maintenance and help protect the appearance of the building. The design is also passive. It does not require an electric motor, sensor, pump, or computer. Once applied, the surface geometry and chemistry perform the work whenever rain reaches the wall. That simplicity is powerful, but the Lotus idea does not stop with buildings. Engineers have explored similar surfaces for glass, metals, fabrics, solar equipment, transportation, and even industrial machinery. Water-repellent textile finishes, for example, are designed to prevent water and water-based stains from soaking into clothing or footwear. HiQ's X-Repel technology is one modern example of a fluorocarbon-free water-repellent treatment for fabrics. Although not every water-repellent product is a direct copy of the lotus leaf, many pursue the same general objective, which is to control how liquids interact with a manufactured surface. Researchers have also created lotus-like coatings for steel and transparent polymers, and these surfaces are being studied for purposes such as corrosion resistance, anti-icing performance, easier cleaning, and reduced contamination. The potential is broad because nearly every industry must manage unwanted contact between a surface and water, dirt, chemicals, or ice. However, this is where an important limitation appears. A natural lotus leaf is alive. It can grow, maintain its wax layer, and replace the damaged biological material. A manufactured coating cannot automatically repair itself in the same way. The tiny structures that create super hydrophobic behavior are also vulnerable. Scratching, abrasion, ultraviolet exposure, harsh chemicals, or ordinary wear may flatten or remove them. Once the texture is damaged, water may begin to stick instead of rolling away. Researchers have identified mechanical and chemical durability as major obstacles to the wider use of synthetic lotus effect surfaces. This directly addresses an important gap between the biological model and the engineered version. Nature does not merely create a useful texture, rather, it supports that texture with a living, renewable system. Engineers often copy the surface pattern without copying the leaf's ability to maintain it. The term self-cleaning can also sound more powerful than it really is. The surface still needs moving water, usually rain, to carry dirt away. It may work very well against loose dust, but less effectively against oils or sticky substances, deeply embedded contamination, or even damage to the coating itself. Experiments with artificial superhydrophobic surfaces have shown that cleaning effectiveness depends on the structure of the surface and the energy of the moving droplets. So, the lotus effect is not a force field. It's a carefully controlled interaction among surface texture, chemistry, water, and contamination. That limitation also points towards the future. Researchers are developing tougher coatings with flexible binders, layered structures, and textures that remain water repellent even after abrasion. Some newer designs attempt to expose fresh roughness as the outer material wears away, almost like giving the coating a limited ability to renew its functional surface. Future applications may combine lotus leaf structures with other technologies. A surface could be water repellent, resistant to corrosion, and able to detect damage. Manufacturing methods such as nanoimprinting and three-dimensional printing may also make microscopic textures easier to produce at scale. The larger lesson is not simply that lotus leaves repel water. It's that useful engineering ideas can be hidden in ordinary biological structures. The lotus plant solved the surface contamination problem without detergents, powered equipment, or human maintenance. Engineers recognized the underlying mechanism and transformed it into coatings and materials that can reduce cleaning, conserve resources, and extend surface life. The copy is not yet equal to the original, however. Artificial surfaces still wear out, and their effectiveness depends heavily on how and where they are used. Yet, that imperfection makes the topic more interesting. Biomimicry is not about copying nature's appearance. It's about understanding its operating principles, identifying what can realistically be manufactured, and improving the design where the translation falls short. The next time rain beads up on a leaf, a jacket, or the side of a building, consider the engineering beneath that small droplet. Sometimes, innovation begins not with a new machine, but with paying closer attention to a plant that has already solved the problem. Thank you for listening to the Lotus Leaf's Hydrophobic Effect.